Hi, welcome everybody. I'm Justin Braaten, developer advocate with the Google Earth Engine team. Today I'd like to talk about harmonizing 50 years of Landsat imagery. This is an exciting year for the Landsat program. It's their 50th year of imaging. And this is an incredible record of Earth change. So what we're seeing here are a couple of animations of a Landsat time series from 1984 to the present. We can see things like on the left there, shoreline changes on Cigar Island in India. On the right is forest change in British Columbia. You can see forest clear cuts and a big open pit coal mine. Lots of other changes like lake level rise and fall, agricultural irrigation in the desert. We've got really dynamic rivers. This is the Ucayali River in Peru. On the left, on the right, we see Las Vegas increasing in size over time. And these are all annual composites, cloud-free imagery from Landsat 5 through Landsat 8 in this case. And if you've worked with Landsat, you've often heard this story about we've got 50 years of imagery, but often what you see in academic research and data sets are the data starting in 1984 and going to the present. So you're often missing that first 10-ish years in the 70s. And so this story about 50 years of imagery is not always what we actually get. So I've been really interested in, I guess before I move on, Landsat 5, has been imaging since 1984 and really the baseline for much of the work that we see. But Landsat began imaging in 1972, so there was 3 earlier satellites that collected MSS data, multispectral scanner. And this is what I've really been interested in, is taking the time series as far back as you can. But that data from the 70s is quite different from the data that Landsat 5 began collecting with the thematic mapper sensor. So the rest of the talk will be about trying to take this MSS data from the 70s and making it look like TM so we can do an analysis on 50 years of data and not just the 40 years. And Earth is constantly changing. There's lots of things happening in the 70s. This is an example from Mount St. Helens, which you see right there, sort of in the center, and up above it is where the volcanic blast occurred. So all of that region that's kind of in yellow, it was the result of the volcano. And what we're seeing here is a 3-band composite of time in the 70s. And so all the pixels that are color, like red, yellow, blues, those have all changed. Everything in grayscale has not changed. And this is just to emphasize that a lot was happening in the 70s that we don't know about if we're not going to look at that era. Before I came to Google, I was working at Oregon State University for a research lab interested in doing forest change detection and modeling forest structure and things like that. And when you look at a time series of Landsat, after, depending on the forest type, 15 or 20 years, the satellite signal is saturated after a clear cut, after a disturbance. So you really don't have a lot of more information after 20 years of growth. And so some people at this research lab that I was working at thought that if we could map disturbances back into the 70s, we would at least know when something happened and would have some more information and more context for what the present is like. And they found success by including disturbance information. They could better predict current forest conditions. And this was just sort of a one-off paper, and my supervisor thought it'd be great if we could do this more often. Can you please automate this process? And so I came up with this system. This original system was in R. So we had to download all of the Landsat imagery. It was still a kind of a pain in the butt. It was run on local computers, downloading all this imagery, running this, all these steps. But it worked. It worked pretty well. And I moved on from this project eventually. But when Earth Engine came around, I was really excited to try to port this functionality of taking MSN imagery and making it look like TM, bringing it to Earth Engine, automate it even further. And so the result at this point is that I have a notebook, sort of a prototype. It relies on the Earth Engine API to do all this processing of the MSS imagery. And what you see here is the notebook. The first half of it is just sort of parameterization and setup of Earth Engine authenticating to it, initializing. The bottom part are 4 or 5 steps to actually do the work. And so basically you can set the parameters, hit run all on this notebook, and in about half a day, you get a 50-year time series of Landsat that is harmonized through time. And so some of the challenges about generating this data are MSS. It only had 4 bands, green, red, and 2 near-infrared bands. So it's missing a lot of the information that later sensors had, in particular SWIR bands, shortwave infrared, and thermal, which contain a lot of information. Some other things that are funky about MSS compared to TM, the later sensor, is the radiometric and spatial resolution. So on the left, there we have an example of MSS data. The shading, there's 64 shades. It was 6-bit data, and also the pixel resolution was larger than TM, which had 8-bit data and 30-meter pixels. So we have these challenges of MSS not looking like TM, both in terms of the data that it collected spectrally and then sort of the degraded sensor qualities. But there's a cool feature about Landsat, the program, that Landsat satellites 4 and 5 carry both the MSS and the TM sensor. So we have this great data set of coincident imagery, the exact same landscape at the exact same time. We have an example of MSS and TM, so we can develop a relationship to help predict TM bands from MSS data. So the first step of this process to get MSS to look like TM is to generate a reference image of MSS from the 80s. So MSS that was on Landsats 4 and 5 is pretty good data. So the first thing we do is make a cloud-free composite from a few years in the 80s of MSS. It might look like this, for instance. And then we take all of our other MSS data, which is generally much noisier than TM and later sensors, and we normalize it to this reference image, just using random forest regression, so we get images that all sort of look like each other to start out with, but they still don't have all of the bands that MSS or that TM has. The next step then is we have these images that look like each other relatively. We remove the clouds from them and build annual cloud-free composites. So we have one image that represents sort of the growing season per year. And now we have this nice set of MSS images that have no clouds in them per year, and we want to draw a relationship between the MSS data and the TM to make MSS look like TM. So we do that with these coincident images. We take these pairs that were collected on the exact same day, the same location. We draw a random sample. This is just 3, sort of examples of what those might be. Random sample. We create a linear regression model with random forest. That's an aggregate of all of the samples that we have for these coincident image pairs. And then we take our MSS images, run them through this model, and out we get pseudo TM data. And so you made this linear regression. Now they look a lot like MSS looks like TM, but you still have this residual around your regression line. So we can clean it up even a little bit further by calculating the mean offset per pixel. So this is an example of 1 pixel's time series. And at the top there, we're showing that there is still this offset in tasseled cap angle space. And we can remove that offset and get them lined up a little closer. And so we do this on a per pixel level. And this is an example of what that offset might look like. And you'll see a lot of linear features in there. And this is sort of the result of MSS having lower resolution data than TM. TM is better able to resolve the edges for roads, clear cuts, streams. So now we'll look at examples of the data, the TM, the good data, MSS, the data from earlier, the poorer data. And at this point, the data have been run through the random forest regression model, no offset correction yet. And you can see they look quite similar. What we're visualizing here is SWIR1, NIR, and green as RGB. And recall that MSS didn't have any SWIR bands, so we can see we've done a pretty good job of getting it into the SWIR space. But it's blocky. You can't see edges as well. The stream is not as crisp. Anytime there's a transition between forest and non-forest, it's sort of blocky and not well defined. After we do the offset correction, you can see that it becomes much more crisp. We can see the stream outline. We can see the utility line in the upper left come up real clearly now, and a little bit more diversity in sort of, the color. And if you look at the histogram of this image, we can see that MSS and TM, their distribution is quite similar for all of the bands. So MSS did not have a blue band, and you can see that we predicted quite well. It didn't have SWIR 1 and 2. We do a little bit less well with predicting those, but get the general trend. And the tassel cap brightness, greenness, wetness are derivative bands. Tassel cap wetness has a large component from SWIR, so it's not as well predicted as greenness and brightness, but it all looks pretty close. So if you're trying to map forest change from clear cuts, for instance, sort of large dramatic change, it does a pretty good job. This is comparing the same image, coincident image pair, TM to MSS. They look quite similar. Maybe in the agricultural region, MSS is a little more muddled. This is looking at the comparison with SWIR 1, NIR, and green. Again, really similar. Here's the coincident pair in true color. And true color includes the blue band, which MSS didn't have, but we can predict it really well, as you can see here. And the last thing that we do to this data is run it through Landtrender to try to clean up any extra interannual variability. So this is an example of a single pixels time series. It happens to be a forest. At the top there, the blue represents a stable, mature forest, and then it gets cut, it turns red in color, and then it recovers. But you can see there's this noise year to year. What Landsat does is it finds these sort of durable events and segments and assigns vertices. And we can interpolate new values between these vertices to get a really nice straight time series. And so we can generate this synthetic time series of MSS through to the present, where everything has been normalized and segmented. And now we can include 1972 to the present. This is a lot of clear cutting in the Pacific Northwest. Blue is mature forest, reddish brown are bare ground, and kind of greenish is recovering forest. This is Mount St. Helens. It erupted in 1980. So we couldn't see, before the blast unless you include MSS. And we can see here that it's quite seamless from MSS to TM era and after. We saw this animation earlier. It's the same location in British Columbia with the open pit coal mine. And by including the 1970s data, we get really close to when it began to open up. This is an example of the Olympic Peninsula in Washington State, forest harvests again. This shows a region in the Forest Service. Let's see if I can show here. This region is Forest Service land. They had a big policy change in 1994. And you can see that in the 80s and the 90s, there was quite a bit of harvesting, and then it stops and regrows. They didn't allow harvesting in this section anymore. And it's nice to be able to include MSS for a little bit more context and a longer history to understand before the policy was in effect. This is showing wildfires in Yosemite National Park. And I think the cool thing to note here is all the harvesting that is happening on the west side of the park in the 70s and 80s. And again, without MSS, we wouldn't be able to see that as well. And so at this point, we've just been looking at synthetic time series data, but what you can also do with the output from running this code is all of the outputs that Landtrender gives you for segmentation. So with these segmented outputs, we can create maps of forest change, for instance. So what we're seeing here is the year of forest disturbance, greatest forest disturbance. So this has been sort of a pet project of mine. The code is available for use on GitHub. There's a notebook there and some instructions. So if you're interested, you can take a screenshot or write down the URL. There's not a lot of support I can give for it, but there's an issues section. If you have questions, I might be able to help you out. But I'm really happy for you to try it in your region of interest. except that it doesn't work well all over the world. This is a map of availability of MSS data. The blues are areas where this system will probably work pretty well. Areas outside of the blue, it's going to be challenging. There's just not a lot of observations. Thank you.